Hello everyone, I am Ayush Kudur from IIT Gandhinagar and I am presenting NILMBENCH 2026, a deployment-aware benchmark for energy disaggregation. This is a joint work with Anurag Singh, Harsh Dhruv and Professor Nipun Batra. Non-intrusive load monitoring, or NILM, estimates appliance-level power from one aggregate smart meter signal. Here, the top plot is the aggregate main signal from UKDale, a public UK household electricity dataset widely used in NILM research. Below it are fridge, washing machine, and dishwasher signals. The goal is to recover those without placing sensors on every appliance. This is useful because smart meter only feedback is easy to deploy, but it's fragile. At deployment time, the model sees only the aggregate signal, and appliance signatures change across homes and devices. NILM is an inverse problem. From one aggregate signal, we recover multiple appliance signals. This can work because appliances leave characteristic signatures in the power trace. The fridge is relatively regular, with periodic compressor cycles. The washing machine is multi-stage: heat, agitate, and spin. Its duration and internal states vary. The dishwasher, on the other hand, is sparse and bursty. It is off for long stretches, then has high power events. A model can predict almost zero most of the time, get a reasonable MAE, and still miss the most important activations. NILM methods have changed significantly over time. Early approaches were combinatorial and event-based. They detect edges in the aggregate signal and match them to appliance changes. Probabilistic models treated appliances as hidden state processes, but scaling them was difficult. Deep learning models such as sequence to point learned signatures directly from data, and transformers brought longer temporal context. This table shows the gap. NILMTK made NILM experiments accessible. NILMTK contrib expanded the model set, but existing benchmarks still didn't cover the deployment questions we care about. NILMBENCH 2026 evaluates 16 models in 2 resolutions and provides efficiency metrics through flops and runtime in both cross-building and cross-dataset transfer. The main difference is that we evaluate the things that matter together: accuracy, event detection, efficiency, and whether the model transfers beyond the setting it was trained on. We use 3 public datasets. Red is collected from US homes, where the main supply is 110 volts. UKDale and Refit are from the UK, where the main supply is 230 volts. The appliance set covers periodic loads such as refrigerators, sparse or bursty loads such as microwaves, and multi-stage loads such as washing machines. We exclude datasets that can't support deployment evaluation, such as single building datasets and paywall datasets. The benchmark has 3 design goals. The first is reproducible ML tooling. Legacy NILMTK installs were brittle: old Python and TensorFlow stacks, dependency conflicts, and broken environments. That made published numbers hard to reproduce. The screenshot shows real installation issues from the legacy stack. We rebuilt the ecosystem as a modern 2026 ML stack: PyTorch models, Docker for reproducible environments, UV for fast dependency management, and a unified NILMTK experiment API, so every model follows the same protocol. NILM has to work at user feedback and utility scale timescales, and deployment means new homes and regions. So we evaluate 1-minute and 15-minute resolutions, sealed cross-building and cross-dataset splits, and both MAE and F1. On the right, comprehensive coverage. We score 16 models across 4 families on MAE, F1, parameters, and flops under one protocol. Here are the 3 deployment tasks. T1 trains and tests on different time windows from the same home. This is the best case setting. T2 trains on some homes and tests on an unseen home from the same dataset. T3 trains on one dataset and tests on another, such as red in the US to refit in the UK. This introduces voltage, country, appliance, and collection differences. So from T1 to T3, we move from fitting a familiar home towards deployment under domain shift. The first finding is that domain shift causes the largest error jump. In this plot, lower is better. T1 and T2 are close, around 33 to 34 watts mean MAE. But in T3, the error rises to about 55 watts. This is the gap we wanted the benchmark to expose. A same home split is useful, but it's still a friendly setting. The appliance signatures and data source are familiar. The real stress test begins when we move to new homes, and especially to a new dataset. In that case, the homes, appliances, grid conditions, and measurement setup can all change. So we keep T1 as a sanity check, but we treat T2 and T3 as the evidence for deployment. The second finding is that ME can hide missed events. These microwave plots show ground truth in blue and predictions in red. Both NILM and sequence to sequence predict almost zero for most of the window. Because a microwave is usually off, this can still produce a deceptively low MAE. But the model has failed. It misses the spikes. Sparse high-power appliances need event metrics such as F1. MAE alone is not enough. The third finding is that more compute is not automatically better. This plot compares cross-building MAE with parameter count. The x-axis is in log scale and lower on the y-axis is better. If size explained quality, we would see a clean trend, but we do not. TCN has only about 69,000 parameters, but matches much heavier models on T2. NILM is compact and strong. RNN attention with classification has about 4.9 million parameters and is worse on average. So the message is not simply to use larger models. The model structure and how well it matches NILM matters more than the parameter count alone. The platform goal is to make new models easy to evaluate under the same protocol. On the left is the basic interface. A PyTorch time series model can be wrapped as a NILMTK contrib disaggregator by implementing training and prediction methods. Once wrapped, the model runs through the T1, T2, and T3 configurations. The output includes ME, F1, parameters, flops, and runtime. This makes comparisons less ambiguous. A model is judged by whether it transfers, detects events, and is practical to run. Let's look at a short demo video showing how a sealed NILMBENCH task is run and how the benchmark reports ME, F1, and efficiency metrics.
One smart meter, every appliance. Disaggregation models keep improving, but do they survive real deployment? New homes? New datasets? Let's test that. We take PatchTST, a state-of-the-art transformer, and turn it into an energy model. Setup is one container, PyTorch, 16 models, and the datasets API. No dependency hell. Wrapping PatchTST takes about 30 lines. You define only the network. Training, windowing, and the sealed splits are all inherited. The whole experiment is one config: datasets, appliances, models, and metrics. Readable and identical for every model. Score it cross-building. We report MAE, F1, parameters, and speed. PatchTST tops the board with 159,000 parameters, not 3.6 million. Now the real test, cross-dataset. Train on US data, test on the UK. Seek to point collapses below the baseline. PatchTST holds up. That generalization gap is the whole point. Add any model, score it on the sealed tasks, and read the leaderboard. That's the benchmark.
To summarize, NILMBENCH 2026 is a deployment-aware benchmark for NILM, and the main lessons are: same home accuracy is not enough. MAE can reward models that miss sparse events, and more parameters do not guarantee better deployment performance. Looking forward, NILM needs a generalization-first benchmark culture, a public out-of-distribution leaderboard, challenge-style evaluation like the KDD Cup, easier model onboarding, and more work on domain adaptation. The project page is shown here, and the code is available through the NILMTK Contrim GitHub page. Thank you.